Yeah. Okay. So, welcome to the APRG seminar today. We are happy to have Utsav Dewan from ISI Kolkata, who will talk about restricted mean value property on Riemannian manifolds. Yeah. Utsav, you can start.
Yeah, thank you, sir, for the introduction, and thanks to the organizers for giving me the opportunity to present my work here. So today I'll be talking about restricted mean value property on Riemannian manifolds, and this is based on a joint work with one of my PhD supervisors, Professor Kingshook Biswas. So let us start by recalling the following characterization of harmonic functions on Euclidean domains. So a continuous function U on a domain, by domain will always be an open connected subset of the ambient space. So a continuous function U on a domain omega in Rn is harmonic if and only if it's for each x in omega, U satisfies the spherical mean value property with respect to the normalized surface volume measure for all spheres S centered at x and contained in omega. So we have this spherical mean value property for all spheres centered at x for all x in omega, so that the spheres are contained in the domain. So this is the usual characterization of harmonic functions in terms of their spherical mean value property. So this motivates one to look at the following weaker version of mean value property, which we call restricted mean value property. So a function U on a domain omega in Rn is said to satisfy the restricted mean value property, which we'll refer to as RMVP, if for each x in omega there exists a sphere Sx centered at x contained in omega such that one has the spherical mean value property. So the key difference between the usual mean value property and this restricted mean value property is that here we are, for each x in omega, we are only assuming that the function is satisfying the spherical mean value property on one such sphere centered at x, not all the spheres that are contained in that domain and centered at x. So it's certainly a weaker notion of mean value property than the usual that of the harmonic functions. So the most natural question is, so if a continuous function U satisfies only RMVP, this weak notion of mean value property in a domain omega in Rn, then is U harmonic in omega. So instead of looking at the spherical mean value property on all such spheres, if for each point one only assumes that that is being satisfied only on one sphere, whether that is enough to conclude that the function is actually harmonic. So in this direction, the first result was due to Kellogg. He assumed, he worked on the special case that omega is a unit disk in R2, and he proved that if U extends continuously to the closure of the unit disk and satisfies RMVP, then U is harmonic in D. So not only is it continuous inside the domain and satisfies RMVP, but also he's assuming that the function is actually extending continuously to the closure, so also to the boundary. Then he's able to conclude that U is harmonic in D. So that is a natural question then, that whether one can actually get rid of this extra condition imposed by Kellogg. But then Littlewood actually has some counterexamples. So without any assumptions on the boundary behavior, there are counterexamples of continuous functions in unit test T satisfying RMVP that are not harmonic. So it's continuous inside and satisfies RMVP, but doesn't have any. If you don't have any boundary behavior assumption, then actually there are examples of such functions which are not harmonic, yet it satisfies all these properties. So, and these counterexamples of Littlewood had some specific property that the functions were unbounded. So then Littlewood posed this following problem, which basically asks whether this unboundedness is the only obstruction. So if one also assumes that the function is bounded, then whether one can do better. More precisely, if U is a bounded continuous function unit is T satisfying RMVP, then is U harmonic. So note that continuity and this restricted mean value property was already there, but in view of his counter examples, Littlewood discarded the situation when the function can be unbounded. So just assumed bounded also. He added the boundedness into the mix and then asked whether it is going to be harmonic or not. So this is the classical Littlewood's one circle problem. And so for n equals to 2, actually the answer is in negative. So there exists a bounded continuous function in the unit is T satisfying RMVP, which is not harmonic. This counterexample was constructed by Hansen and Adidashvili. So, but for n greater to 3, the Littlewood's one circle problem is still open. So their counterexample was very dimension specific. Okay. So anyway, even for n equals to 2, one can see that the answer is negative. So it's bounded, continuous, and RMVP. These three are not enough to conclude that the function is going to be harmonic. So of course, one would like to add some more sufficient condition. We are trying to just keep on adding condition and to see when we actually get a positive result. Yet that we are not assuming as much as Kellogg did. He assumed that the function is actually continuous up to the boundary. So we are not going up to that much, but still we are trying to just keep on adding condition and to see when we get a positive result. So again, the only positive result we have seen so far is due to Kellogg, who assumed that the function is actually, when the function is actually continuous up to the boundary, then the function becomes harmonic. So one would be naturally inclined to give this fourth condition as some boundary behavior condition. And so what would be the most obvious choice of boundary behavior if you're not allowed to take the continuous extension on whole of the boundary? So the most naive choice would be that the boundary limit exists on a full measure subset of the boundary, right? So, and as it turns out, this is actually enough to conclude that the function is harmonic. So you start off with a bounded continuous function in your dis D that satisfies RMVP. And in addition to these three conditions, you also assume that you have the boundary limit. Boundary limit exists for almost all points of the unit circle. Then actually the function is going to be harmonic. So when you add this extra condition, which says that the boundary limit exists on a full measure subset of the boundary, then the function actually turns out to be harmonic. So this is the result of Fenton, which we would like to see in a more general setup. So, firstly, we would like to see in the most general setting of bounded domains in a general Riemannian manifold.
Okay, so I have a small question here. Actually,
yeah, sure. Go on.
You are assuming that this bounded limit z going to e to the power I theta, uz exists for almost all theta. Okay.
Right.
But the thing is, if u is bounded and continuous function on D, that means radial limit will exist, right? For almost all theta. I think so. So in that sense, you are really, in this Fenton's result, you are really taking some strong condition. Do you get my point, what I'm saying? Hello? Hello, am I audible?
Yeah, Muna, I can hear you. I think Utsav probably has lost connection. Or... hello, Utsav? Okay, we'll wait for Utsav to. Muna, you have his contact number or something?
I'm calling him.
Yeah. Okay.
Yeah, so
I think Utsav is not back.
Yeah, the internet issue. Yeah, sure. Yeah.
You have to.
Yeah, I'll continue with Munada's question. Okay, yeah. Is it fine now?
Yeah, we can see the screen. Yes.
Yeah, Munada, please go on with your question.
No, what I am saying that if you use a bounded continuous function in D, so this is probably comment. Probably that means radial limit will exist.
No. For a bounded continuous function, I don't know such a result.
No, it need not.
It need not
harmonic
functions,
right? It would.
Yeah.
H infinitive D. Okay. Sorry.
No, you're not. That's what you're trying to. You say.
Sorry. Okay. It may.
This is an inverse problem. Okay, so let me rephrase the problem once more, since there is some doubt.
No. I understood now. Okay. So sorry. Sorry. Okay. For harmonic function, it will exist.
Yeah, for harmonic functions it exists. So we are trying to see. Yeah.
No, that's okay.
Okay. So any more questions, or should I go on?
Go ahead.
Go on.
Okay, fine. So yeah, my objective is that this is Fenton's result. Okay, and this for the unit disk in R2. Now one would like to see generalization of this. We would like to generalize this. Like the most general setting would be bounded domains in general Riemannian manifolds. So that is our first stoppage. So yeah, but before posing this problem of restricted mean value property or even trying to get hold of a Fenton type result, first thing one should know is that what is the natural mean value property for harmonic functions in general Riemannian manifolds. So in a Riemannian manifold M, it is not true in general that harmonic functions satisfy the mean value property over geodesic spheres with respect to the surface volume measure induced by the Riemannian metric, unlike the case of the Euclidean spaces. The mean value property does hold, however, if one replaces the Riemannian measures on the geodesic spheres by the harmonic measures on the spheres. So actually the spherical mean value property does hold true, but for a different class of measures, namely the harmonic measures. So what are harmonic measures? So for a bounded domain omega in M, say with sufficiently regular boundaries, say C2 boundary and del omega, one has for any x in omega, you consider this evaluation map. So Ex is take a continuous function phi on del omega and look at U phi. U phi is the harmonic extension of phi on this domain. So the Laplacian of U phi is identically 0 in omega, and U phi agrees with phi on the boundary. So you look at the harmonic extension phi U phi and evaluate it at x. So this is a linear map, and it would follow from the maximum principle that this is actually a positive bounded linear functional from C del omega to R. Okay, that's a simple consequence of the maximum principle. Now you have a positive bounded linear functional on C del omega. So, and this is a pre-compact. So del omega is compact. So as it turns out, that then now you can just simply use Riesz representation theorem to write this evaluation map. This can be represented by means of a Radon measure. So there exists mu x omega on del omega, so that for all phi continuous on del omega, you can actually write this. So the evaluation linear functional can be represented in terms of the boundary value in this integral with respect to this harmonic measure, these measures mu x omega. Okay, so these are what we call the harmonic measures. Okay, so because these are you're getting the harmonic extension by integrating the boundary value with respect to these measures. So yeah, so this harmonic measures are generalizations of the Poisson kernel. For instance, the unit disk you're working, you have an explicit expression of the Poisson kernel. So these are the generalizations of that. So let us look at more properties of the harmonic measures. So these are probability measures. So that's very easy to see. You just put the boundary condition to phi identically 1. Then this right hand side is the total mass of this harmonic measure. And what is the left hand side? So if you look at a constant 1 function, its harmonic extension will be the constant 1 function again, right? So this left side will be 1. So the total mass of these measures will be 1. So these are probability measures. So it's as simple as that. Okay. The next thing is that for you take a bounded domain omega in M, these harmonic measures are actually mutually absolutely continuous with respect to the surface volume measure induced by the Riemannian metric. So although in the general case of Riemannian manifolds, harmonic functions and domains, they don't satisfy the spherical mean value property with respect to surface volume measure induced by the Riemannian metric, but they do it for harmonic measures. But these two measure classes are not too they belong to the same measure class actually. So they are mutually absolutely continuous. So they are not too far off from each other. And now comes the geometric notion of injectivity radius. So we are in a Riemannian manifold. So for P in M, you look at the injectivity radius at P. So what is that? So this exponential is the Riemannian exponential. So Riemannian exponential at P, this would be a map from the tangent space TPM to the manifold M. Now we know that for any general Riemannian manifold, this is a local diffeomorphism. So for each point P, you look at the TPM tangent space and the zero vector of the tangent space that gets mapped to P under this exponential map. So since this is a local diffeomorphism, we just keep on looking at small balls in the tangent space around the zero vector and see up to which point it is actually diffeomorphic onto its image, and you take the supremum. So up to the stage, it actually is diffeomorphic onto its image. So that's hence the name injective radius. So up to that point, it is a true diffeomorphism. Okay. So within the inject radius at P in M, the metric spheres. So you have a Riemannian manifold, you have a Riemannian metric that would give rise to an inner metric, and that will give rise to the metric spheres, right? You have a metric space, you can define spheres there. These metric spheres centered at P are nothing but geodesic spheres. So by geodesic spheres, I mean that in the tangent space, if you look at spheres, and if you look at their image under the Riemannian exponential map, they will be these metric spheres. So these are going to be C infinity submanifolds of the manifold M. So remember that in our previous slide, we were talking about we're talking about this del omega to have smooth, sufficiently regular boundary, right? C2 boundary. And as it turns out that if you stay within the inject radius, these spheres are actually C infinity submanifolds. So one actually has that the Dirichlet problem is solvable, and also there are harmonic measures. And this leads us to the mean value property, formulation of mean value property for harmonic functions in Riemannian manifolds. So a harmonic function U on a domain omega in M satisfies for all x in omega this spherical mean value property. Instead of the usual surface volume measure, we have the harmonic measure here, and the spheres can't be too large. Of course, the closed balls have to be contained in omega. That's only it will make sense. Moreover, the radius has to be strictly smaller than the injective radius, because then only the spheres will be C infinity and one actually have harmonic measures. So these measures are well defined only in that sense. So up to this point, whatever we have done, so the upshot is the following. You just choose your spheres sufficiently small so that the radius is smaller than the injective radius at x, and you just replace the usual surface volume measure by the harmonic measure. That's what you get for a general Riemannian manifold, a harmonic function. This is what the mean value property is. So that's the only difference we are encountering. Then this leads to the reformulation of the restricted mean value property. So a function U on a domain omega in M is said to satisfy the RMVP for each x in omega. You have a radius Rx, which is smaller than the inject radius at x, such that the closed ball Vx, Rx closure is contained in omega, and you have this spherical mean value property. So just in the Euclidean case, so we look at the usual mean value property of a harmonic function in a general Riemannian manifold, and instead of looking at the spherical mean value property for all such spheres, we only, for each x, we fix one Rx, and we look at the sphere with center x and Rx radius. So only for each point x, you just look at one sphere, and hence this is the restricted mean value property, the natural analog of the restricted mean value property for a general Riemannian manifold. Okay. And this brings us to our first result. So let M be a Riemannian manifold, and let omega in M be any precompact domain with C2 boundary, such that the distance from x, del omega is strictly less than the inject radius at x for all x in omega. So these are the technical conditions which I was mentioning, that one has to have nice control over the radius of the sphere so that it's smaller than the inject radius, so that one actually get harmonic measures. And so these are just the technical conditions, and in particular one can see that any geodesic ball will be satisfied in omega. So Fenton only worked for the unit ball, so these omega can be much more like less symmetric. They can be like very distorted domains, but still just satisfy this geometric condition. Now this is just a geometric condition. The next line is simply the most natural generalization of Fenton's result. So if U from omega to R is a bounded continuous function that satisfies RMVP in omega, and the boundary limit exists for almost every giant del omega with respect to the Riemannian measure on del omega, then use harmonic. So it's bounded, continuous, satisfies RMVP, and has boundary limit on a full measure subset of the boundary with respect to the Riemannian measure on the boundary. Then use harmonic. So this is the most natural generalization of Fenton's result in this more general setup of Riemannian manifolds. So next stop, we'll look at in the global case and also see the proofs. But before that, I'd like to stop and ask if there are any questions. Munada, any questions?
No, you carry on. I will ask some question at the end.
Okay, that's great. Anyone else have any question? So maybe I should go forward now. Yeah. So this is the local setup. This is our result. The next stop, of course, this is for bounded domains in general, Riemannian manifolds. But one would like to see that if this is a local result, one would like to see a global analog of that. So, for instance, like on a hyperbolic space or anything, because there we know, unlike in the Euclidean case, in those sort of spaces, negative curvature, there are bounded non-trivial harmonic functions, right? In the Euclidean case, it's not, but in negative curvature, we have that. So that prompts us to look at this sort of manifolds. So let X be a Hadamard manifold of pinch negative curvature, which means that there is a complete simply connected Riemannian manifold with sectional curvature bounds between two negative constants. Kx, the sectional curvature, is between minus b square and minus a square for some 0 strict less than a less or equals to b. Okay. So for these sort of spaces, what are the examples? So any rank 1 Riemannian symmetric space of non-compact type is an example of such a space. So you take G by K. So G is a connected non-compact semi-simple Lie group with finite center, rank 1 of course. And you look at its maximal compact subgroup K, and you consider the quotient G mod K, then that's actually going to be a rank 1 Riemannian symmetric space of non-compact type. And this is actually a particular example of the class of spaces we have considered here. And for such a space, due to its negative upper curvature bound, actually the injective radius is infinity. Okay, so for each point we were considering up to which point the Riemannian exponential is going to be diffeomorphic onto its image or not. So for these sort of spaces, it's globally diffeomorphic. So no issues there. So you can like take spheres as large as you want. The Euclid problem would be solvable. And now comes the most important notion of chroma boundary, because in the previous result also we saw that there is some boundary behavior is associated with all these sort of results, and one would like to get hold of a nice boundary. So one has the notion of chroma boundary. So it's defined in the following way, that the set of equivalence classes of geodesic rays in X, where you take two geodesic rays. So by geodesic rays, I just mean an isometric embedding from the half line close 0 open infinity to X. Okay, you take these sort of geodesic rays and you look at the equivalence class of them, where two geodesic rays are equivalent if distance of gamma 1t, gamma 2t for all positive time t, this is bounded. So they are asymptotically close to each other. They are not too far off each other. So that is the meaning of this statement. And when you have that these two geodesics are equivalent, then you look at the equivalence. This is the way you look at the equivalence class of such geodesic rays, and you'll get the notion of chroma boundary. And of course, one would like to have a nice topology on the space attached to this boundary. So there is actually a natural topology on X closure. X union is chroma boundary called the cone topology, such that that topology makes X closure into a compact metrizable space, which is a compactification of X. Okay. Now, one would of course like to see whether there are nice measures on the chroma boundary, because that is the point.
Can you go to the last one, previous slide?
Yeah.
Okay. So there is a natural topology next one. Okay. Okay.
So whether one actually has nice measures on the chroma boundary, because we would like to see whether, like on a full measure subset on the boundary, we want to talk about something. We have got hold of the boundary, we have got hold of the topology where we can say that it's going to the boundary in a certain sense, the cone topology. And important notion now, one would like to see whether this boundary actually has plenty of interesting measures. So again, we look at the Dirichlet problem. So for phi continuous on the chroma boundary, whether there exists a unique, of course, if there exists a solution to the Dirichlet problem by maximum principle, it's going to be unique. So whether there is a harmonic extension U phi, which is continuous on the X closure and C2 in X, so that Laplacian of U phi is 0 in X, so it's U phi is harmonic in X, and U phi coincides with phi on del X, so that this Dirichlet problem is solvable or not. And as it turns out, this is the case. So Dirichlet problem is solvable, and this was shown by Anderson and Schoen. And the moment one has that the Dirichlet problem is solvable, one gets for free the class of harmonic measures, right? One has the mutually absolutely continuous family of probability measures, namely the harmonic measures. So now there is this key difference between Riemannian in the bounded domain situation and this full space setup. So as I had told there, that in case of a bounded domain or Riemannian manifold, so the harmonic measures and the Riemannian measure, they are actually mutually absolutely continuous. But these measures in this full space situation, in case of pinch negative curvature, these measures need not be mutually absolutely continuous with respect to the geodesic measure class on del X. So what do we mean by geodesic measure class? So the del X, the Gromov boundary, is actually homeomorphic to the unit sphere, Euclidean unit sphere. It's C alpha homeomorphic with alpha depending on these curvature bounds. So so the point is a very geometric construction. So you look at the unit sphere, you look at any geodesic starting from, you fix an origin in the space O, and with respect to that you look at the unit sphere around it, and then from the origin, I mean, you'll start off with any geodesic that has the initial velocity is some v in the unit sphere Sn minus 1. Then you carry on with that geodesic for infinite time, and it will hit some point on the Gromov boundary that you look at, that you call as v plus. So in this way you get a radial projection map from the unit sphere to the Gromov boundary. And this radial projection map is going to be a C alpha homeomorphism. So this, under this C alpha homeomorphism radial projection map, one has of course the usual Riemannian measure on the unit sphere, and you can simply look at the push forward of that under this radial projection map, and that will give rise to another measure on the Gromov boundary. That is what you call the geodesic measure class. So with respect to different origins, you get a class, because here also it depends on the harmonic measure case, also it depends on the interior points. So in this way you get that. But these measures need not be mutually absolutely continuous. That is the caveat. But in the special case, when X is a rank 1 Riemannian symmetric space of non-compact type, they actually belong to the same measure class. So so you look at the compact picture of a rank 1 Riemannian symmetric space, so of non-compact type. So you look at the Karta decomposition, and then you can actually identify G mod K with K mod M cross A plus closure. And in that polar decomposition, the Gromov boundary you can actually identify with the Lie theoretic just K mod M. K is the maximum compact subgroup K of G, and M is a centralized of A in K. And that actually there again, that's the special case of this sort of spaces, and there actually these two measures coincide. So in this more homogeneous setup of symmetric spaces, this actually are the same measure class. Okay. So in this setup with like these sort of challenges, we still have this result. So let X be a Hadamard manifold of dimension greater equals 2, satisfying this sort of pinch negative curvature condition. So the sectional curvature is between two negative constants for some 0 strictly less than A less equals to B. Now this is just the analog of Fenton. So let U from X to R be a bounded continuous function satisfying RMVP such that you have this extra boundary behavior condition. So Ux limit X goes to psi exists for almost every psi in del X. So this limit is in the cone topology with respect to the harmonic measures on del X. Okay, here the harmonic measure class and the geodesic measure class are separate, may not be the same. So we have to specify which measure class we're talking about. And so again, it's bounded continuous and satisfying RMVP, and has boundary limit on a full measure subset of the boundary with respect to harmonic measures. Then U is harmonic index. So this is our result in the full space setup. Okay. So now we look at some key ingredients of the proof, and I would like to emphasize that these sort of things are either not, I mean, it's the point is that these are extremely trivial in the case of Euclidean spaces, because as I mentioned at the very beginning that the unit disk T, these harmonic measures just simply are given by the Poisson kernel, and you have explicit expression of that. So whatever we are going to do next for the next few slides, those are extremely easy in the case of Euclidean unit disk, where you have explicit expressions of the Poisson kernel. But here, in this more general setup, actually you don't have any sort of explicit expression. You have to do certain estimates, certain different kinds of things, and we are going to do all of this. And all of these are completely new and totally different from the Euclidean case. Okay, so the first point is the concentration of harmonic measures. So let me just give you the statement, and then I'll give the heuristic what's happening. So let omega in M be a domain with C2 boundary. Okay, so you start off with a domain with C2 boundary in the manifold M, Riemannian manifold, and now let psi, you fix a psi on del omega. You fix a psi on its boundary del omega, and let U be a pre-compact neighborhood of psi. Okay. Now, what the next few lines mean is basically you have fixed a point on the boundary, and you have also fixed a pre-compact neighborhood of psi. Now, so inside this neighborhood, we are going to have this sort of condition that basically you have a local C2 deformation of the domain near psi. So Gn is a sequence of C2 local diffeomorphisms from U into M, with Un defined by Gn U, satisfying Gn of U intersection del omega to be Un intersection del omega n, with the boundary getting mapped to boundary, the insides getting mapped to insides, and Gn converges to identity in C2 norm on U. So it's a local C2 deformation. Okay, so near psi, this pre-compact domain, pre-compact neighborhood, you have U, you basically do a local C2 deformation because Gn is converging to identity in C2 norm on U. But that is the point. Outside of U, what is happening, we don't care. Outside of U, it can be very wild, all these sequence of spaces, okay, omega n. Outside this UNs, it can be totally wild, whatever you want to have, but it's not going to affect the concentration of harmonic measures. So what do I mean by that? So if you take xn in omega n such that xn converges to psi, then this convergence of points would give this convergence of measures. So you look at for each xn in omega n, you look at the corresponding harmonic measure mu xn comma omega n. This will converge to the Dirac at psi weakly. So first of all, in the particular case when omega n is equals to omega, so there is no deformations going, it's just a constant space. So in that case, it's very trivial. It just follows from the Dirichlet solvability of the Dirichlet problem that this harmonic measures converge to Dirac at psi. But when we are also perturbing the domains, it's slightly non-trivial. And more interestingly, this actually, for those people who are familiar with the properties of the Poisson kernel, that it's an approximate identity and so on, the mass is, we know that for an approximate identity, the mass is concentrated. And so basically, this is what's happening. You have this corresponding convergence of harmonic measures, which basically gives you the concentration of so that mass is being concentrated, that phenomena is being generalized here. You can say like that. Okay, so this proof of this fact is actually uses local barrier argument. So for each such omega n, you have psi n, right? You just consider Gn of psi. So under these Gn diffeomorphisms, you look at where psi goes, you call it psi n. And for each omega n, you construct a superharmonic barrier function near psi n, and then you can estimate the harmonic measures. You can basically see that outside the neighborhood, it's the harmonic measure is asymptotically going to 0. So hence it is concentrated in that neighborhood, and now you can consider that neighborhood to be arbitrarily small near psi. So basically it's going to converge to Dirac at psi. So this follows from local barrier arguments. So this has a global analog as well. So let X be a Hadamard manifold of pinch negative curvature. Now let Wn be a sequence of domains in X where Wn is either a ball, a hollow ball, or the full space X. So okay, we understand what is a ball and what is a full space. Now what is a hollow ball? So again, let's go back to the simplest case of a rank 1 Riemannian symmetric space. So we know that when we look at the Uyasama decomposition of the group and so on for the space, we look at the n orbits in the compact picture. Yet we look at the n orbits; they give the hollow spheres, right? And so how are we getting that? as a geometrically or theoretically, whatever you want to say, theoretically more precisely. So you have the Euclidean A projection map, and these horospheres, these are given as the level sets of the Euclidean A projection map. And hence the horoballs are simply given as a sub-level set of the Euclidean A projection map. And for these sort of general Hadamard manifolds of pitch negative curvature as well, one actually has the notion of the notion of Boltzmann functions, and these Boltzmann functions generalize the Euclidean A projection map in suitable sense, and you can look at their level sets. They would give you the horospheres, and sub-level sets will give you the horoball. So that is the horoball. Now these Wn closures converge to W closure in the Hausdorff topology and complex X closure, where this limiting domain W is either a horoball or the full space X. Now, if xn is in Wn such that xn converges to xi for some xi in W closure intersection del x, then again this convergence of points would result in the convergence of measures. So here again, the limiting domain is either a full space or horoball. So if W is a full space exposure in del x, so then xi can be any point on the Gromov boundary. But if W is a horoball, then the closed horoball actually intersects the Gromov boundary at a unit point. So the base point of the horoball. So that this is xi. So one would get this sort of convergence in measures. So the key difference between this result and the previous one.
Could you repeat the previous point?
Yeah, the horoballs.
Yeah.
Yeah. So we know that even for rank 1 symmetric space, if you try to picturize that, you look at a horosphere in the compact picture of the symmetric space, then the closed horoball. Okay, so that horosphere is that's a level set of the Euclidean projection map. You look at the sub-level set, so the area enclosed by that horosphere. Now you look at the compactification. So you look at the interior as well as the boundary horosphere. All of that intersects the boundary at infinity at a unique point, right?
Yes, yeah.
This is that is the only choice of xi when W is the limiting domain is the horoball. That's what I'm saying. Fine. Okay. So the key difference between this result and this is the global setup and the previous local setup is that note in the previous setup, the local setup, we are only assuming that these we are perturbing the domains locally near xi. Outside that fixed neighborhood, what is happening, we don't care. But here, and that local deformation was C2. But in this setting, we are actually assuming that whole of these Wn closures are converging. So we are assuming something more, but in the weaker sense, just in the Hausdorff sense, not in the sense of C2. So it's a much weaker sense of convergence of domains, and that would result in the convergence of harmonic measures. And this now follows from global barrier argument. So now we can actually construct global barrier functions on the negatively curved manifold using the upper curvature bound. So recall that the sectional curvature was assumed to be less or equals to minus a square. And using that a, one can actually, and doing some basic comparison results, one can actually explicitly construct some global barrier functions. And then again, one can estimate the harmonic measures. So this was the first ingredient, that is concentration of harmonic measures. The second thing is that convergence of Poisson integrals. So here the rough idea is that you have a sequence of domains again. So again, is either in the local situation, that is a pre-compact domain in the Riemannian manifold M, or it's in the global situation. So D is a Hadamard manifold of pitch negative curvature. So both the cases we're considering. So you consider a sequence of domains Wn in D, so that Wn closure is converging to W closure, and as well as its boundary del Wn is converging to del W in the Hausdorff topology on compacts in D closure. Okay, for some domain W in D. So again here, so the point is this, that you start off with here, you be a bounded continuous function on D, satisfying this sort of boundary limit condition on a full measure subset of the boundary. Okay? So on the full space D, you start off with a good function U. It's bounded, continuous, and also it has like nice boundary limits on a full measure subset of the boundary. Now, in that ambient space, you look at these sort of sequence of domains whose closure as well as their boundary, they converge in the Hausdorff topology on compacts in D closure. Now, for each such Wn, you look at the Poisson integrals of U and Wn, meaning that we look at the harmonic extensions of U and Wn, they would converge pointwise on W, the limiting domain, to the Poisson integral of U and W. So simply, in simple terms, if you have on a big space, if you have a nice function satisfying these sort of certain properties, and inside the ambient space, you have a sequence of domains that converge to some other domain, then for that sequence of domains, you can consider the corresponding sequence of harmonic extensions, right, on all such domains, because U is bounded. So just as an as an L infinity function, the Poisson integral makes sense. Actually, it's continuous, but okay. So
Naru, are you able to hear? I think.
No, I think he lost connection again. So we'll wait for him to come back.
you get a sequence of harmonic functions.
So we lost connection for 1 or 2 minutes, 1 minute probably. So can you repeat it a bit? Oh God. Utsav, are you able to hear?
Okay, so let him rejoin. Utsav?
Yeah, it's fine now.
1 second. Okay, now I can see this.
Yeah, plenty of internet interruptions.
Yeah, sure, no problem.
So it's like Brownian motion techniques. So what I was trying to say is that so far all we have seen is analytic interpretation of properties of harmonic measures, right? They give us a solution to a Dirichlet problem. But on the to all of this. Okay, so these are the Brownian modes. So what I mean to say is that say in the two cases we are considering, so either a precompact domain in a Riemannian manifold M or a pinch negative curvature situation. So look at the Laplace Beltrami operator is essentially self-adjoint on such spaces, and so say CC infinity X being the dense subspace, underlying dense subspace, and then one can actually look at a unbounded self-adjoint extension to all of. So I mean, is it working? Is like, am I?
Yeah, but you can make it full screen.
Yeah, sure.
Okay, good.
Yeah, like sometimes I'm getting confused when I'm connected or not. So yeah.
Okay.
Yeah. So the point is that like in all these situations, bounded unbounded self-adjoint extension to all of L2x, and then corresponding to that you get a heat semigroup. Now, due to these assumptions on the space, this heat semigroup is actually going to be very nice. So it's what's called a Feller semigroup. So it's going to be a contractive, positive family is a semigroup of strong operators of strong SOT operators, and then also it will satisfy. Okay, so that Feller semigroup, the heat semigroup is going to be a Feller semigroup, and then one can actually correspond to that to a Markov process. One can associate a Markov process to any Feller semigroup, and that Markov process is besides the Brownian motion we're talking about. Now, since we are talking either a precompact domain in a Riemannian manifold M, or we are looking at a negatively curved manifold, this Brownian motion is always going to be transient. Look at a point. So it's look at a point, any point, and almost surely the Brownian motion will escape that space. So, and this, what is the connection with the harmonic measure? So the distribution of the first exit point of this Brownian motion, that will be given by the harmonic measures. So use that probabilistic interpretation of harmonic measures as well to get this sort of results. And finally, we look at the L infinity maximum principle. So again, either we are in the local setup or in the global setup. And now let phi be a bounded continuous subharmonic function on D such that limit x goes to xi, phi x equals to f xi for almost every boundary point xi with respect to the harmonic measures on del D. So the point here is that we will get a pointwise domination of phi x with by the Poisson integral of its boundary values. Okay. So the point is that here it doesn't matter what, like here only we know that the boundary limit for on a full measure subset of the boundary, okay, for almost every boundary point to shine. And despite of that, we are getting this maximum principle. So that's why we are calling it this L infinity maximum principle. Now, it's not only a L infinity maximum principle, but it's actually something more informative in the following sense that this is actually the least harmonic measurement of this subharmonic function phi. Now, for those people, these sort of least harmonic measurements, potential theory in Euclidean spaces, one would know that actually in the unit disk also, you look at concentric spheres, and so that they increase up to the unit sphere, and then they just look at the corresponding harmonic extensions on each of these spheres, each of these balls, and they just take a limit. And then by harmonic and so on, one can actually conclude that that converges, and that is going to give the Poisson integral. But in that will not be the case, because the geodesic measure, that limiting process will only give you the end result, the measure will be just the geodesic measure class, but that need not be consistent, that need not be in the same measure class with the harmonic measures, so that one won't necessarily get this Poisson integral. So for this, we have to come up with a completely different approach, and again we use Brownian motion technique. So now, armed with all these results, now we can finally start the sketch of the proof. So the idea is very simple. We had that function u, which was continuous bounded, satisfied RMBP, and also satisfied certain boundary behavior. Now one would like to see whether that is actually harmonic or not. So the idea is simple. Idea is to construct two and w, and to squeeze u between v and w. Okay, so v in this way, one would construct v will be actually continuous bounded subharmonic, and w will be continuous bounded superharmonic. So this is a superharmonic function, this is a subharmonic function, and u is squeezed between them. And one would actually try to conclude that v is actually equal to w. Then u will be v, so you will be subharmonic, you will equal w, so you will be superharmonic, so you will be harmonic. But how are these v and w constructed? So let's go back to previous slide. So this is how they are constructed. So for fix the point z in the space, and now consider this family of collection of harmonic extensions of u on balls bxr. So where x is in omega, r is less or equal to dx del omega, and z is in bxr. So all those balls that contain z, okay, and these balls are not just any balls, but their boundary spheres are special in the following sense. On the boundary sphere, actually, you have this, it satisfies the restricted mean value property. So you, for every z, you look at all those balls so that the balls are containing z, and their boundary sphere actually satisfy the spherical restricted mean value property with respect to harmonic measures. So recall that for every point x, we have such a ball. So these are those balls, and we are looking at the harmonic extension. So look at the harmonic extension on only those balls. This is in the local setup. For the global setup, you look at similar balls, and also you have to look at hollow balls and the full space X, because in that situation, it's going to be a pre-compact family. So if you take the limit of only these balls, it won't basically simply in negative curvature. If you look at the host of convergence of balls, they need not be a ball. It can be go to the full space. They can degenerate to a point. They can converge to a ball, of course, but they can also converge to hollow balls. So we have to take this into account as well. So in this way, we end up with these two functions. V is a continuous bounded subharmonic function, so that for each set there exists h in f set, so that vz equals to each set. and W. So this not only that they are continuous bounded subharmonic, but in the definition of V, we are actually looking at a supremum. And what our result says that for each set, actually one can find some H in FZ, this family, so that the supremum is actually attained at that point. And similarly for W, the infimum is attained at that point. And U is actually squeezed between V and W. So all of these follows from application of concentration of harmonic measures and convergence of Poisson integrals. So we have got hold of this phi and W, and U is between them.
So I think your screen is frozen.
Okay, where in which slide are
so you are on 16, slide 16.
Oh, I'm currently in 17. Okay.
Yeah. So the definition of V and W, I think, yeah, I would like to see that.
Is it now working?
No. Maybe you can share again, close it and share again. Yeah.
Sure. Now is it working? Sir, now is it working?
No, it has not appeared yet. Just give it a second. So.
Hello, sir. Now is it working?
No, I don't see it. Anybody, Amuna, can you see it?
No, I have not.
Oh, I see. Okay.
No, I am not able to see it. Okay, so
yeah, I'm also not able to see the shared screen.
Maybe you can. Okay. Share once more.
Hello, sir. Now is it working?
Not yet.
Okay, so do one thing. Just leave and join once more time.
Yeah, maybe exit and log in again. Perhaps that will work.
Hello, sir. Now is it working?
No, not yet.
So, have you shared the screen?
I can't hear anyone.
I think it's better.
Yeah, so am I audible?
Yeah, audible.
We can hear you.
Just share the screen once more.
Yeah, now is it visible, sir?
No, I still can't see the shared screen, and it is still blank.
Okay. Yeah. So should I rejoin or do something or?
Yeah, I think it's
maybe try to rejoin.
Yeah, go out and then rejoin and then start from the beginning. Yeah.
This is a bit strange. Why it didn't happen?
Yeah, no, it may be something to do with the connection.
Maybe.
Is it now working?
No.
No.
I can't see it.
Oh. Yeah, maybe
they want to slide to somebody, Nina or something. One of us can try to share.
Oh yeah. Okay, you can send me the slide.
Okay. Yeah, sure. Yeah. First of all, I should stop sharing them. Hold on.
So next time onwards, I will ask the speaker to give the slide so that if there is something wrong, I can.
There is only one next time, I think. Yeah.
That's next time.
This semester.
We have only one more talk. Right?
So Apurva, when do you want to start the next APRG seminar?
Sorry, what?
So we want to start the next APRG seminar in the next semester, right? So when do you want to start?
You said something like July or something. Our semester starts in August, but you decide.
July or
No,
June?
I think
June.
I think everybody
Anyway,
has.
you don't. Anyway,
No,
I
June,
can
July
join
is July end will be okay, but
That's what I was saying. Our semester starts in August.
August, yeah.
Maybe end July.
Yeah, maybe
something.
August first week is better.
No.
Yeah, so you have sent me the slide thing?
Yeah, I've mailed you to ISC, your ISC mail.
Okay, just wait. No, it has not reached it. So.
Okay.
Oh, now, yeah, of course, it is now. I got it. Okay, so I should start sharing, right?
Yeah, that
download. Okay.
Yes, yeah.
Okay, let's cross our fingers.
So are you able to see my screen?
No, you are not shared, so you
You're
probably
not
opened
shared.
it. There is that upward arrow, right?
Yeah, I am doing that.
Yeah, if you were doing your icon would appear on the screen, but I'm seeing all the 6 icons of the people present.
Yeah.
So your sharing has now not started.
The download.
Yeah, sorry for the trouble.
Yeah, that's okay.
Yeah,
it will happen.
that's okay. That happens. But Utsav, where are you? At ISI or?
Yeah, ISI.
So there is some serious internet issue there, or?
Yeah, I guess so.
Okay, so this is the page. Okay.
Munna, you have not shared anything.
God. I have shared. I have. So desktop or window. I have shared, but
maybe share the window and then choose the group.
I'm doing that.
Well, we don't see anything. I see.
Okay, so Mike.
Can you see my window? Can you see a graph with some trees?
Yes. Apurva, we can see yours.
Okay.
My sharing works, so maybe send it to me.
Yeah.
Okay.
Send it to me.
Sorry. Okay.
I don't understand why.
Yeah. I see.
Got it. 1 second. I still don't understand what's going on. Some of you. Munna is an owner in the teams now, so it should also be. Okay, now let's see. So first of all, okay. Let me share. Share screen window. Press share. You can see this.
Yes.
Yes. Yeah.
Yeah. Fine.
Okay.
It's
So
fine.
now I'm going to
So I guess on slide 17, I guess.
17, yeah.
Yeah, go on.
Yeah. So again, so that's what I was saying, that we look at those harmonic, those families. Families was clear, Naru sir?
Yes, yeah.
So you look at the pointwise supremum and infimum of that. So these V and W will actually be continuous bounded V will be continuous bounded subharmonic, and W will be continuous bounded superharmonic, and you will be squeezed between this V and W. And this follows from concentration of harmonic measures and converse of Poisson integrals, as discussed before. So please go to the next slide.
Next slide, sorry.
Yeah.
I'll just put like this so that it's easier.
Yeah, exactly. So okay, so we have got those V and W. Now the point is simple, that if you start off with a good point xi on the boundary. So here I'm just saying boundary because in case of the bounded domain, it's just a topological boundary. In case of this negative curve space, it's just a Gromov boundary. So irrespective of that, so when you have a good point on the boundary, that is limit says z goes to xi uz equals u xi, then it's the same for V and W as well. So xi continues to be a good point of V as well as W. So limit z goes to xi Vz with the same boundary value u xi, same for W. So this follows from concentration of harmonic measures and converse of Poisson integrals. And finally, step 3 is that we wanted to show that V and W are actually equal. So we consider this difference function phi to be V minus W. This will be bounded continuous because recall that W was dominated by V, so it's non-negative, and V was subharmonic, W superharmonic. So this difference will definitely be subharmonic function. So that phi actually vanishes on a full measure subset of the boundary, because it follows from the previous step, right? Because V and W have the same boundary limit on a full measure subset of the boundary, so that their difference will vanish on the full measure subset of the boundary. And then I think it's not, maybe the next thing that it's actually how it follows. So there is an elementary maximum principle that would show that actually all that matters is what happens on the full measure set. So if phi vanishes on a full measure subset of the boundary, so actually phi is identically 0. And thus U is equal to V as well as W. So U is harmonic. This would follow from the L infinity maximum principle we had discussed before. Yeah, so I'm basically done. So just let's move to the next few slides and just bibliography. Yeah, so yeah, I'm really sorry that all these internet issues were there. But like, if still after all of this someone feels interested, they can visit our paper. It's the highlighted one. And there's like full details, etc. And yeah, one can also find these references in this book of Rudian as well. So yeah, thank you for your utmost patience.
Okay, thank you, Utsav. It was a good talk, even though there were all these technology issues. So any questions?
Yeah, I have 2-3 questions. So the thing is, here this phantom's result actually. So you have assumed that the thing is for any point on the boundary, this the limit
A full measure
right?
subset of the boundary.
Okay, so the thing is, so what happens if you remove that condition? That suppose you assume only radial direction it is exist, because see that seems to me very natural. Means that is a necessary condition.
Yeah, for related to these sort of like more restricted boundary behavior, there is another preprint on archive. You can visit that of mine. That addresses these sort of questions. Yeah.
So you have done something, right? If you really take only radial convergence, right?
Not really radial, because radial I think is too much to ask. Like I have done for non-tangential limits, which is the most natural boundary behavior assumption for harmonic functions.
Okay. Another thing.
So that's a separate preprint. You can visit that on archive. Yeah.
Okay. So two things. This Hadamard
Sure.
manifold of pinch negative curvature you were taking. I think that this injectivity radius is infinitive, right? For this kind of
That's even more true for non-positive curvature. So if kx is lesser or equals to 0, that's enough to get that. Yeah.
Yeah, that's right. And another thing is this kind of so the example which you are really basically saying this rank on symmetric space of non-compact type, right?
Sure.
But I think this if something is a symmetric space and this has really pinch sectional curvature like the way you have really stated, I think that is precisely rank on symmetric space of non-compact.
No.
There is a result. I remember I have seen some kind of result like this.
No. Let me give you the statement what I mentioned there. That if you take a rank, so you take a rank one symmetric space, rank one Riemannian symmetric space of non-compact type, that will satisfy the pinching condition. Okay. And what are you saying? Can you please repeat your question?
Oh, if there is a say higher rank symmetric space, okay, any symmetric space of non-compact type, which has really pinched sectional curvature, then that is precisely a rank one symmetric space.
Actually, for higher rank, yeah, that is true. Because higher rank symmetric spaces, actually there can be the sectional curvature can vanish in certain directions. So for pinch negative curvature, yeah, it's just rank one setting. Okay, because if you go to higher rank or even Dame-Cauchy spaces, for instance, there can be like sectional curvature can vanish in certain directions. So it will become non-positively curved, not necessarily pinch negatively curved, but what I thought your question was that about this sort of how big this class is, that you look at a Hadamard manifold of pinch negative curvature and you look at rank on symmetric space, how big this complement is. I think that was one your question maybe. So
that's what I wanted to ask.
That I can give you a very easy example. You can like construct this like very easily. So you start off with, say, for instance, real hyperbolic space, okay? And you look at it, so it's basically constant negative curvature -1 or whatever. Okay. Now you look at a small neighborhood, small ball in the space, okay? And in that portion, you bring some, like, you look at a bump function which oscillates very much in that small ball, and you multiply the metric, Riemannian metric, by that. So because the bump function vanishes on the boundary, outside that small ball, there is no distortion of the Riemannian metric, but inside it does all sorts of oscillation, right? And what would that do? That would simply kill all the global isometries. It will kill like trillions of global isometries. Okay. And the group isometric group will become very, very small. That is my point. So what I can say you that, you know, of course, that rank one Riemannian symmetric spaces, these, the main reason people work on these is because it has a rich isometric group, right? It has a very nice structure, this semi-simple Lie group with finite center and all that. But for a general pinch negative curvature setting, the isometric group can only be a discrete group gamma. Okay. For the Stringers theorem, any isometric group is actually a Lie group, a finite dimensional Lie group, but it need not be so nice as something like a symmetric space. It can be a discrete group. So for that, it's like, you can understand the situation is drastically complicated than in a rank of symmetric space.
Yeah. Okay, so I don't have any question, but the thing is, okay, so this Kellogg and this Hansen's result, which you are really saying, okay. So what is the idea of that thing? Is that proof is very complicated?
Okay, Kellogg's result is rather easy. It's easy. And Hansen and actually they construct a counterexample of a function which is bounded, continuous, satisfies restricted minimal property, but is not harmonic, right? That was the statement I mentioned. So they construct a counterexample, and it's like 14-15 pages of construction of that function using random processes, using probability theory. So it's quite involved, to put in a simple statement.
Okay, thank you for that. I don't have.
Thanks to you.
So just a simple question or a silly question. Some of these questions make sense for higher rank symmetric spaces, right?
Yeah. That would be I mean, like the higher rank symmetric space. Yeah, I mean, for their like, they're also, although they're not. That's a valid question at least. Yeah, we haven't.
One has a different kind of mean value property.
Yeah, because those spaces are not harmonic manifolds. So yeah.
But because of Fustenberg and so on, we have some results. Yeah, but I wasn't sure how to even formulate
But that is a
that
global, actually Furstenberg boundary is a global boundary to infinity.
Correct.
But in case of here, we are also like interested in the local behavior, because we have to keep on asking these local harmonic extensions, right? So it's again going to be the similar, the harmonic measure situation. Yeah. Yeah. So yeah, that is that, like you just change the setup to higher rank non-compact symmetric spaces. Yeah, that is a relishingly interesting problem to maybe try out. But we haven't got any result in that. Yeah, that's a very interesting question. Thank you, sir. Thank you for pointing out.
Yeah. Yeah. All right. So, any other questions? Yeah. If not, let us thank Utsav for a nice talk. So, yeah. Thank you very much. Yeah.
Yeah. Thank you. Thanks all of you for your patience. Yeah.